Well, good afternoon. I just want to put this up. I reopened this because people were having some difficulties accessing it or submitting it. So what I want to do is take a couple of minutes and go through it and just give you some clues as to what's going on here. Let me take a look here. Question one. This is actually measurement and conversions. This is very rudimentary. They're talking about something on a triple beam balance. Now you might say, what's a triple beam balance? Let me see if I can get a picture of one here. Sure we can. Okay, perfect. This is something that we don't use too often. We have digital balances now, and a balance is a way for us to get the mass of an object. You might say the weight. I'm going to weigh something, but that's not technically correct because when we're measuring in grams, we're actually measuring the mass, and there is a relationship between mass and weight. And as long as we're always making our measurements on Earth, we can kind of use the terms interchangeably. But I'll explain more about that when we need to. If you take a look here, this is called the triple beam balance. And you would put your object or chemical or whatever whose mass you wish to find on this pan. And if it's a chemical, of course, you'd put it in some sort of a thing called a weighing boat and you'd zero that out. And then you would slide these masses over, these weights over, if you will, until this thing balanced out back at zero. Hence the name a balance, okay? Not a scale, but a balance. And it's all based upon this idea of balancing this out. So even the digital scales, if you will, we call them balances. So when you go ahead and look at the quiz, they would say, okay, let's take a look at this. You have something on there. What is the mass of the object? 374.123. Okay, and if you put 374.3, that's okay. But really, what you need to do is estimate that last one place past the last decimal place. Now, this looks like the little notch is right on 4.3, so we would actually call that 4.30. So let me see if I can do this without getting myself in trouble. Whenever you do this, if I can measure, I forget what was the mass. I forget 300 and I don't remember 374.3 grams. You really want to also make your best guess at that one place after that. So you actually can have what are called five significant digits here to use for calculations. So that's one thing to keep in mind. Another is when we're going down here. That's my next question. Oh, I guess I better answer it. This is not letting me just go through and do it. 374.30. See if they probably won't count that as correct because, but that's okay. Now, same thing with this. You can read this graduated cylinder 10, 11, 12. The meniscus is right on 12.0 milliliters. So if you were going to write that, you go ahead and say, well, I can read to 12 perfectly fine, and I have to estimate one place after the decimal point. Now that's something that they don't give the option for the answer on that, but to be correct, you really should do that. And of course, if you write 12 milliliters on this little online quiz, you're correct. But when we get into the laboratory, you really do want to make it a habit of getting that decimal place one past where you could read. Like for example, if I have a grad cylinder here, well, it's not a very good looking grad, it looks like grad cylinder someone kicked in here. And this might be, I don't know, 10 and 15. And so this would be, for example, if my water level was, my meniscus was kind of like right between two lines, this would be 10.6, 10 point, or excuse me, 10, 11, 12, 13, oh, come on, 10, 11, 12, 13, 14, 15.5. 5. So we would call that 15.5 milliliters. You get to estimate that last decimal point. Very bad drawing, and I apologize for it. But I'm trying to use a very primitive setup here. Okay, so let's just call this 12 and move forward. And it says convert this temperature to Kelvin. Well, I maybe should have given you the conversions for this if you don't know them already. I shouldn't make an assumption that you do. So let me get a fresh piece of paper here. Oh, there we go. The old camera fell down. I don't know how these people like on YouTube get these really nice programs to use. I'm stuck here with a piece of paper and some pens. But anyway, let's talk about Kelvin. Kelvin temperature is the absolute scale of temperature, Kelvin. And with the Celsius scale, the one that we use quite a bit in chemistry, it has negative numbers. 0 Celsius, and then you have negative numbers, negative temperatures, positive temperatures. We need a temperature scale that is an absolute temperature scale, where the coldest temperature you can possibly have is 0 Kelvin. That's not okay, that's 0 Kelvin. And it goes up from there. So there are no negative temperatures. When you'll see the reason and the great utility for this when we start doing calculations, especially in gas laws. You have equations like this: V1 over T1 is equal to V2 over T2, where V is volume and T is temperature. And if we just use Celsius, we could have a 0 temperature. And if 0 is in the denominator, one of these things becomes undefined. If I have negative temperatures, well then I would end up with negative volume, so you just can't have that. So we have what's called the absolute temperature scale, and the coldest you can get is 0 Kelvin. That's negative 273.15 degrees Celsius. So you can't get any colder than that, because at 0 Kelvin, all of your molecular motion stops, and basically we're all done. So we can't ever get to that temperature. We can get very close in a laboratory. But the conversion is degrees C plus 273.15 gives you Kelvin. Now, it's not degree Kelvin, it's just Kelvin. Kelvin is that unit. So when you see something like that, you're going to be converting from Celsius to Kelvin. That's a very simple calculation. All right. So I look at this, and it looks like negative 20, and then 1, 2, 3, 4. Boy, these eyes are getting old here. 1, 2, 3, 4, 5. So this is negative 22. Say like negative 24. So you would take 273 minus, what did I say, 24? And I get 249 Kelvin for my answer. Okay, convert the thermometer temperature to Celsius. Well, this is a excuse me, a thermometer in Kelvin, and I've got 60 degrees, so I would add 273 to that. Okay, 273, what's that, 333? Let's see what happens. Okay, metric conversions, you should be really very, very used to these by now. If I want to go from milliliters to liters, I just divide by 1,000. If I want to go from kilograms to centigrams, well, you'd have to go ahead and do a series of conversions for that. And let me show you how to approach that. We know, well, hopefully we know that kilo means 1,000. Okay, and centi, like centimeter, means 1/100th, okay, of whatever my base unit is. So I am going from 0 point. Oh, let me bring this up a little bit here. I'm going from 0 point. No, I can't see my thing here. Let me copy down the problem. 0.0000052 kilograms, and we want to get this to centigrams. Okay, so let's go back to this. Let's go back to this full screen. So what are we going to do? Well, first of all, I would go from kilograms to grams. How do I do that? Well, easy. I set up conversion factors. I know that there are 1,000 grams in 1 kilogram. So my units of kilogram would cancel. I would just multiply across the top. But I want to get to centigrams. And I know that there are 100 centigrams in 1 gram. And then we can go ahead and do this. So this is 10 to the 3, and this is 10 to the 2. So I'm multiplying this number here by 10 to the 5. So without a calculator, 1, 2, 3, 4, 5, that's equal to 5.2 centigrams. And hopefully that's one of the answers, unless it's a short answer. Yeah, it's a short answer. So, but anyway, hopefully you're seeing that. Well, I guess you're going to make me go through all of these. Hopefully this is going to be helpful a little bit. All right, let's just go ahead and do this. All right, my answer for that one, what did I say it was? Divide by 1,000, 10, 100,000, 5.8 liters. And this one here is going to be 5.2. Ooh, it's raining out. And to go from joules to kilojoules, you divide by 1,000, so that's 34. Okay, these are some conversion factors. What do we use to get how many minutes are there in 4.2 hours? Well, you want your hours to cancel. So you want your hours in the denominator. So 4.2 hours times 60 minutes per hour. Any of these other ones don't make sense. I mean, there aren't 60 hours in a minute. There are 60 minutes in 1 hour. So there's your conversion factor. Okay, which conversion factor should be used to correctly begin this step 2 conversion? Well, we want to go from liters. It says how many molecules are there? Well, what do we have? We don't have a relationship between liters and molecules. We have a relationship between liters and moles. Okay, so first things first, we want to say 1 mole over 22.4 liters. That will give us the number of liters, and then of course we can use that to get our molecules if we wanted to. So 1 mole is 22.4 liters. Precision. Precision versus accuracy. Okay. Accuracy means you're really close to the target where you want to aim at, or whether that's a measurement in a laboratory, a bullseye, whatever. So you could say, wow, you're pretty accurate here if you're aiming for the bullseye. It looks like all 3 arrows are in the bullseye. And precision means how good is your grouping. If any of you have ever done target practice, you could have, maybe all of your arrows right here, right? And they're all grouped together. So you'd have really good precision, but poor accuracy. You could have just scattered all over the place. Then you have both poor accuracy and poor precision. So in this case, you've got good precision and good accuracy because you're grouped well and you're right in the center of your target. Okay, now kilogram to ounces, you might have to look up this conversion factor. It's about 28 grams per ounce. Double check that though. So you go from kilograms to grams and then grams to ounces. Down here you've got kilometers to inches. Well, there are 2.54 centimeters in 1 inch. So you'd have to work through those conversions. Those are some that you may need to look up. 2.54 centimeters is 1 inch. And there's about 28 grams. I don't remember the exact decimal point. I always look it up. 28 grams is 1 ounce. And but again, that's one that you can look up easily enough. So I'm not going to do these conversions, and it's not going to let me go forward. But doing these things just keep some of these things in mind. These are not perfect. These quizzes, they're generated by someone on Teachers Pay Teachers, and I just purchased the package. So if you're doing okay with these, I'm going to tweak them up a little bit, and I'm going to give you some lessons to go along with each of them. Don't forget, next is density. And I should mention that density is something called an intensive property of a material. And what that means is density is inherent in the material itself. It doesn't change. If I have a block of aluminum that's tiny, tiny little block of aluminum, it has a density of 2.7 grams per cubic centimeter. Density is mass over volume, and that's density. So it doesn't matter. I could have a little tiny piece of aluminum. Its mass to volume ratio is 2.7. I could have a piece of aluminum as big as my head, and it would still have the same density. So I think your next little lesson is on density, and you can call this D is equal to M over V, and be able to solve it. If I want to know volume of something, volume is just going to be mass over density. If I want to know the mass of something and I have its density and volume, volume times density is equal to mass. It's all the same equation. It's just manipulated a little differently. So have fun. If you run into some problems, please feel free to reach out and email me. And that's about it. So talk to you soon.